66 million years ago, Earth supported diverse life, including dinosaurs. The Cretaceous period ended abruptly when a 10-kilometer-wide asteroid struck at around 20 kilometers per second, forming the Chicxulubcrater. The impact site was a shallow marine carbonate platform, part of a tropical sea covering what is now the Yucatán Peninsula. Water depths ranged from 100 meters at the western edge to over 1,200 meters northeast. Below lay 3 kilometers of limestone, dolomite, anhydrite, and shale, all sitting atop 35 kilometers of ancient continental crust rich in granite. This geology would amplify the catastrophe. When the asteroid struck at a 45 to 60 degree angle from the northeast, it released energy, between 10 to the 23rd power and 10 to the 25th power joules, equivalent to billions of megatons of TNT. The explosion dwarfed all human nuclear weapons combined. A fireball hotter than the sun engulfed the sky, vaporizing rock and seawater instantly, launching debris into orbit. In the late 1970s, geophysicists Glen Penfield and Antonio Camargo worked for Pemex, scanning the Gulf of Mexico for oil. Penfield analyzed airborne magnetic data and noticed a strange bullseye anomaly, 180 kilometers wide, with concentric rings. Onshore gravity maps from the 1940s confirmed it, a circular structure unlike any volcanic formation in the region. Penfield believed he had found an impact crater, but Pemex dismissed the idea, favoring volcanic explanations. Corporate policy blocked data release. Though Penfield and Camargo presented their findings at a 1981 geophysics conference, few attended. Most experts were at Snowbird, Utah, debating the cause of mass extinction, unaware the answer was already mapped. Houston Chronicle journalist Carlos Byers wrote a front-page story about Penfield's discovery, but it vanished into obscurity. Without physical evidence like shocked rocks, the claim lacked proof. Penfield sought drill cores from Pemex wells, including one from 1951 that hit a thick andesite layer, possibly impact note rock, but the samples were lost. Discouraged, he abandoned the search. Meanwhile, in Italy, geologist Walter Alvarez and his father Louis, a Nobel-winning physicist, studied a thin clay layer at the kpgboundary in Gubbio. They found iridium levels 160 times above background. Iridium is rare on Earth but common in asteroids. Their 1980 science paper proposed an impact event, yet many paleontologists rejected it, citing the 3-meter problem, a lack of fossils near the boundary suggesting gradual extinction. Almost simultaneously, Jan Smit in Spain reported the same iridium anomaly. Global findings followed. Over 2,000 papers were published in the 1980s. But without a crater, the hypothesis remained incomplete. The scientific community searched oceans, misled by glassy spherules thought to indicate open water impact. The real crater lay hidden beneath sediment and bureaucracy. At the University of Arizona, graduate student Alan R. Hildebrand pursued evidence in Texas along the Brazos River. He found greenish-brown clay enriched in iridium, shocked quartz grains, and tiny glass beads, tektites. These form only under extreme heat, like asteroid impacts or nuclear blasts. Nearby, chaotic rock layers suggested violent sediment transport, evidence of a cataclysm. Hildebrand believed the impact was nearby. When Florentine Moras in Haiti found glassy material in KPG layers, Hildebrand tested it, more tektites. He realized the Caribbean was ground zero. But where was the crater? Then, in 1990, journalist Carlos Byers told him about Penfield's buried structure under the Yucatan. Hildebrand contacted Penfield. Together, they secured 2 drill cores from Pemex wells stored in New Orleans. The samples revealed shocked quartz and impact melt, definitive proof. The rocks had undergone pressures exceeding 100,000 atmospheres, transforming minerals in ways only asteroid impacts can. Satellite images analyzed by California researchers revealed a ring of cenotes, sinkholes, centered on Chicxulub Pueblo. These formed as groundwater dissolved weakened rock around the crater rim, a scar left by the bolide shockwave. The 180-kilometer ring matched Penfield's gravity data. The crater was real. In 1991, Hildebrand, Penfield, Boynton, Camargo, and others published their findings, identifying the Chicxulubcrater. Named after the nearby town, its pronunciation, Chicxulub, was a playful jab at skeptics who had dismissed it for years. This was not just a crater, it was the epicenter of Earth's last great mass extinction. Dating the impact required precision. In 2013, scientists used argon-argon dating on tektites from Haiti and bentonite in Montana, calculating the age at 66,043,000 plus or minus 11,000 years ago. A 2015 study of tephra in the Hell Creek Formation confirmed it. In 2018, spherules from Gorgonzola Island, Colombia, gave 66,051,000 plus or minus 31,000 years, within error of the others. The clock of deep time had been synchronized. Even the season of impact was deciphered. At Tanis in North Dakota, sturgeon and paddlefish bones preserved in ejecta-bearing sediments showed annual isotope cycles. The growth patterns indicated the impact occurred in spring, northern hemisphere, late March to early May. Life was beginning its annual resurgence when catastrophe struck. The crater itself is buried under 1 kilometer of sediment, estimated at 200 kilometers wide. Newer studies suggest it may be 300 kilometers across, with the 180-kilometer ring representing an inner wall. Only Chicxulub, Redefort, and Sudbury are this large. But Chicxulub is unique. Its peak ring remains intact and accessible, offering a direct window into impact mechanics. The impact unleashed unimaginable forces. Winds exceeded 1,000 kilometers per hour near ground zero. A transient cavity 100 kilometers wide and 30 kilometers deep formed in seconds. The rebound created a peak ring, mountains of uplifted rock collapsing back into a circular formation. Tsunamis over 100 meters high radiated across the Gulf, scouring coastlines. Firestorms ignited across continents. Vaporized rock and sulfur aerosols entered the atmosphere, blocking sunlight. Photosynthesis halted. Global temperatures plummeted. The impact winter. Acid rain fell as sulfate compounds mixed with water. The food chain collapsed. Within weeks, 75% of species were gone. Non-avian dinosaurs perished, along with plesiosaurs, mosasaurs, ammonites, and many land plants. But not all life died. Burrowing animals, freshwater species, and seed eaters survived. Mammals, then small and nocturnal, found opportunity in the ruins. From this bottleneck, a new world would emerge. In 2010, 41 international experts reviewed 2 decades of data: geology, paleontology, climate models. They concluded the Chicxulub impact triggered the KPG extinction. The evidence was overwhelming. Yet debate persists. Some, like Princeton's Gerda Keller, argue the Deccan Traps volcanism in India, massive eruptions before and after the impact, played a major role. The Deccan Traps released millions of cubic kilometers of lava and gases over hundreds of thousands of years. But a 2013 study compared isotopes in Chicxulub, impact glass, and KPG ash, both dated to within experimental error of 66 million years. The impact was synchronous with extinction. Volcanism may have stressed ecosystems, but the asteroid delivered the final blow. Today, the Chicxulubcrater lies buried beneath the Yucatán. It is one of the largest known impact structures, alongside Redefort in South Africa and Sudbury in Canada. But unlike those ancient eroded scars, Chicxulub's peak ring is preserved, offering scientists a chance to study how impacts shake planets. Core samples from the peak ring revealed granite uplifted from 10 kilometers depth, fractured and mixed with melt rock, confirming models of how large impacts deform planetary crust. The Chicxulub impact caused a mass extinction, including the end of non-avian dinosaurs. It marked a major transition in Earth's biological history, altering the course of evolution. The Chicxulub impact shows Earth is subject to cosmic events. While asteroids still pose potential threats, scientific understanding of such impacts has grown significantly.